Hello and welcome back to Deltek's Physics 111 Exam 2 Preparation and Practice Exam covering forces and energy. In this video, we're going to cover the steps for solving free body diagram force problems, and then we'll actually go through a couple examples of the free body diagram force problems. So if you look here at the top of the page, there's a list of steps for solving free body diagram force problems. And the first step is to draw a free body diagram. Well, what is that? Well, first you draw your system. It could be a box, it could be a person, but it's easiest just to draw a dot representing whatever your system is including, the things that you are interested in discovering how they move and what forces are acting on them. And then you just draw arrows to represent all of the forces acting on that object or system of objects, and you always draw the arrows coming away from the object because they're acting on that object. And then once you've made your free body diagram, you want to make sure you label those arrows with the types of forces, and then you're going to fill the names of those forces or the abbreviations in something called a force table. It's also referred to as an XY table. And this table will have boxes in it that refer to the horizontal forces, the so-called X direction forces, and the vertical forces, the so-called Y direction forces. And then there'll be separate boxes or not, you may create them yourself, for the positive and negative direction in horizontal and in vertical. We usually say that the positive direction in horizontal is to the right, the negative direction is to the left, and as far as vertical goes, moving up is the positive direction, and moving down, or forces down, is the negative direction. And once you've got your free body diagram created and you've filled in your force tables with at least the abbreviations for the forces, then you can start doing your calculations. And the simplest calculation is going to be calculating the weight of the object, the F sub g, the gravitational force on that object. That is the weight of the object, and that is just mass times little g, usually 9.8 meters per second squared. We typically make that negative 9.8 meters per second squared, just to represent the direction, but you can add the negative signs in later. And occasionally you'll get problems where g is rounded to 10 meters per second squared or negative 10 meters per second squared. So you calculate your weight force, and that's pointing down, so that will end up being a negative value. And then if you have the coefficient of friction, the mu, that Greek letter in this formula for friction, you can multiply mu times the normal force, once you determine the normal force, to get the frictional force. And if you don't know the mu value, the coefficient of friction, you can just write the formula. The force of friction equals mu, the coefficient of friction, times the normal force. And then once you've done that, you can start solving for the various other forces, the net force in particular, a net force in the X direction, a net force in the Y direction, by just adding up the X forces to get the net force in the X direction, adding up the Y forces to get the Y force in the net Y force. And these are just sums of forces. That sum of forces and net force means exactly the same thing. Just make sure you remember which forces are negative values and which one are positive values before you start adding them. And once you've determined the net force, if there's a net force that's not zero, in other words, there is a net force, all you have to do is divide it by the mass that you already knew early in the problem to get the acceleration for that object. And that will tell, and the direction of the net force will be the same as the direction of the acceleration. And some helpful hints here. I have some helpful hints for when you're doing motion that's in the horizontal direction, like a box sliding on the ground, or in the vertical direction, say a parachutist who hasn't opened up their parachute yet and is falling from the sky, and hopefully will eventually open their parachute. So let's look at the horizontal motion hints. First, you're going to solve for the weight of that object or individual or whatever it is your system is composed of. M times G gives you the weight. Then you figure out the normal force. Well, the normal force is pressing up against the weight. And if there are no other vertical forces, the normal force will be the same magnitude as the weight force, except the normal force will be positive, pointing up, and the weight force will be negative, pointing down. And once you have the normal force, if you know the coefficient of friction, mu, you can just multiply it by the normal force and get the friction force. And that's an easy way to get three of your forces right away. Okay, now if the object is not accelerating upward or downward, which is probably the case of a box sitting on the ground, well, then the net force in the vertical direction, in the y direction, is going to be zero. That's how you know that the normal force and the weight force have the same magnitude. They cancel each other out. One is positive, one is negative, they add up to zero. If the object is at rest or at constant velocity in the horizontal direction, that is the x direction, well, then the net force is zero also in that direction. That might be the case where nothing is happening in the horizontal direction, or maybe you have a situation where it's being pulled with an applied force, but there is a friction force in the opposite direction that is exactly equal to the applied force. The two forces cancel out, so the object can be at rest, or it can have a constant velocity, even when, especially when the net force is zero. So let's look at the vertical motion hints here. If there's no floor or surface below, in other words, an object is dropping from the sky, there's no normal force. There's no supporting force lifting that object up or keeping it from penetrating the ground. It's just falling. There is still a weight force. There is still G, the acceleration due to gravity, acting on that mass, so it has a weight. The weight is still m times g. Now, when the object starts to fall, the very instant it starts falling, air resistance hasn't built up. Air resistance is just friction with the air as it's falling. But if the object hasn't quite started to actually fall, no air resistance has built up yet. So the only vertical force would be the weight at the instant the object is dropped. Now, as the object is falling, it will build up speed and it will build up friction with the air. And as it does that, air friction increases. Air friction is air resistance. And that is a force that is counter to the force due to gravity, the weight force. So you have a weight force pointing down and air resistance pointing up that is initially zero, and then it gets bigger and bigger and bigger and eventually matches the weight of whatever object or person is falling in the sky. At that point, eventually the net force is zero. But before that, in the very beginning, when there's no air resistance, the net force is the weight force. And as the air resistance builds up, the net force gets smaller and smaller because more and more air resistance is starting to cancel more and more of the weight, eventually canceling it completely. At that point, when they have canceled completely, now you have no net force. But up until that point, there is a net force and there is an acceleration down. It used to be the acceleration due to gravity, little g, but now it's just getting smaller and smaller to other values that we'll just call a, but a is changing, and eventually a becomes zero. Okay, let's start with the first example problem. A 56 kilogram box is pushed with a force of 320 newtons in the positive x direction, means to the right. The box accelerates to the right, but it does not accelerate up or down. The coefficient of kinetic friction, mu, is 0.27, and we're supposed to use g equals 9.8 meters per second squared, negative if it's pointing down or to the left. And we're always supposed to remember to include all units, and that's always going to be true of any physics problem. So we have a dot here to represent our box, and we're going to draw our arrows coming from the dot. And we see the problem says a 56 kilogram box. Okay, it has mass, so being on Earth, the box will have weight as well, and weight is F sub g, the gravitational force. So we'll make a note of that. Straight down. There's our F sub g. There we go. And we are told that it's being pushed. The box is being pushed with a force in the plus x direction. Well, that's an applied force to the right. We have an applied force to the right. And we're told the box accelerates to the right. Okay, well then the applied force is doing something. It's not completely canceled out. And then it also says that the box does not accelerate up or down. Well, if it's not accelerating up or down, and we have the downward force of weight, of force of gravity, then there must be an upward force counteracting it. Well, it's probably sitting on the floor or the ground or something. So we have a normal force that is balancing our gravitational force. Is that everything? Well, we look at the last sentence in the question. The coefficient of kinetic friction is 0.27. Oh, we have friction. Well, if it's accelerating to the right, that means it's moving to the right, and therefore our friction force must be to the left. It's always opposite of the direction of movement or possible movement. Okay, so let's take a look at the force table that we have. Scroll up to it, and maybe I'll just make the screen a little smaller so we can see everything. And it's asking us for the forces in the x direction, the plus and the minus x direction, forces in the y direction, plus or minus. So let's fill them in. Our force in the positive x direction is our applied force. So let's put in our applied force, and we happen to know what that is. We can fill it in here, or we could fill it in later down below, but this is the important part, and it's 300, and that's in the plus direction. We'll give it a plus. The forces in the minus direction, in the x direction, would be the force of friction. And we haven't calculated yet, but we know it's equal to mu times the normal force. And it's going to be in the negative direction. We have to remind ourselves to make it negative. Our net force in the horizontal direction will be equal to the applied force plus our negative version of our friction force, which we know is a negative value. And our forces in the y direction, we know that the negative y direction, it's our weight force. It's the first thing we wrote, and we know that's equal to m times g. And because the only vertical forces are the force due to gravity and the normal force, and they've canceled out, we know that because it's not accelerating up or down, we know that the normal force, which is pointing up, is just the negative version of the weight force. I'll just put a little minus sign to remind us there. And we also know that the net force in the y direction is 0. We know it can't be anything because it's not accelerating up or down. Well, you notice for part B, it says show all calculation work either in the table, we don't have a lot of room here, or on the next page. So what we want to do is continue to the next page and do all our calculations. And you'll notice we have a whole page for that. If we scroll down to the very next page, it says calculate the net acceleration on the box. So ultimately, we're determining the acceleration on the box, and there are a number of things we're going to have to calculate along the way. And so let's let's take account of what we know and what we need to calculate. So what we know the mass. The mass is 56 kilograms. We do not know the acceleration. We do know the coefficient of friction is 0.27, and these don't have any units, so we're not going to worry about units. Our acceleration is question mark for now. And we were also given an applied force, which we know is in the positive direction, and that is 320 newtons in the positive horizontal direction, meaning to the right. Well, what do we still have to figure out? Well, we still have to figure out the weight force, and the weight is pretty easy. It's just m times g. M times g is 56 kilograms. Terrible, 56 kilograms. A little trouble here getting it to appear. And then times 9.8 meters per second squared. That's our g value. And we can put g over here on the side as well, minus 9.8 meters per second squared. So I left off the minus when we did the calculation, but we put it in, and then we keep it in mind that it is going to be a negative value, whatever we get. We have 548.8 newtons. And we'll put the minus sign in there, right there. And we'll put a note that this is going to be a negative force. And since we know that the normal force and the gravitational force, the weight, are the only forces that are in the vertical direction, and they cancel each other out, we know that the normal force is going to be also 548.8 newtons, but pointing in the up direction. And we know that friction can be calculated from the normal force. I'm sorry, that's supposed to be an F. It's the coefficient of friction times the normal force, which is 0.27. Scroll that back up. 0.27 times our normal force of 548.8 newtons. And that will equal 148.176 newtons, which we know is in the negative direction because it's friction. And then, so now we have all the individual forces. We know the value of the weight force, the applied force, the normal force, and the frictional force. And now we put them together, and I'll just draw a little line to separate it. We know that the net force in the y direction is 0, so we're not going to worry about that. So we have the net force in the x direction, which is equal to the sum of our two x direction forces. We have a applied force in the positive direction, and we have a frictional force in the negative direction. So that's 320 newtons minus the 148.176 newtons that we just calculated for the frictional force. We take the difference, and we now know that our net force, it's in the x direction, is positive 171.824 newtons. Well, the only thing we have left to calculate here is our acceleration. And we know acceleration equals our net force divided by our mass. Well, our net force is plus 171.824 newtons, and we know our mass is 56 kilograms. So now we just plug these numbers in and we divide it out, and we end up with our final acceleration as positive 3.068. We know accelerations are always going to be in meters per second squared. And that is the last item that we needed to calculate. So scrolling back here, I want you to see what happens is we have a number of values that we may or may not be given in the beginning of the problem. So they could be things like gravity, which are going to be given, minus 9.8 meters per second squared. And I know I have it written below here, but I just wanted to group these four things together. These are the non-forces that you need to concern yourself with. You might be given two or more of these items, maybe have to solve for one of them, like the acceleration, or solve for the coefficient of friction. You'll generally be given an applied force, and then you have to calculate the values for the other forces, like the force of weight, the weight force, the normal force, and the frictional force. And then once you have those, it's really quite simple to calculate your net forces. You're just adding up the positive and negative values of the individual forces. And then once you have that, you literally just divide it by the mass to get the acceleration. And it's a positive number, which makes sense because you're told right in the beginning of the problem that it's accelerating to the right. And that's the end of that problem. So that was an example of a typical horizontal motion free body diagram problem. So let's scroll to the next problem, and you see it's about a parachutist. So now we're going to be talking about vertical motion, and we'll be dealing with vertical forces. So the problem says an 840 Newton parachutist leaps from a very tall bridge. And for this problem, we're going to assume that G is negative 10 meters per second squared, so not the 9.8 that we usually use. The parachutist does not open the chute until later, which is in part D. All right, so at the instant she begins her jump, there's no significant air resistance force. Well, that makes sense. The moment she leaps off of the bridge, she hasn't started to move downwards at the exact moment. And because she's not moving downwards, she doesn't create friction with the air as she's moving downwards. So we wouldn't expect any air resistance at the very instant she begins to make her leap. Now, at that moment, since there's no air resistance, the only other force that's on her at this point is her weight force. And you're told exactly how much she weighs, 840 newtons. You'll notice this time we were given her weight, not her mass. So be very careful when you see newtons, it's a force. And if you see kilograms, it's a mass. All right, so you're asked to draw a free body diagram at this very instant at the beginning of her jump. Well, what do we have? We have her weight force because she always has weight, as long as she's not in deep space. All right, and are there any other forces? Well, there are no horizontal forces, so we don't need to worry about that. And the only other vertical force we might have is air resistance. But you're told at the very beginning of the jump, since she hasn't started moving technically, there is no air resistance. So this is the entire free body diagram. The only force on her is F sub G, her weight force. So her net force is her weight in this case. All right, so the next question says, what is her acceleration at this moment? Well, the acceleration, we always know, is calculated as the net force, or sum of forces, divided by her mass. Well, you were never given her mass, so we have to determine her mass. Well, we know that her weight is equal to m times g, and we know g is this value, and we know her weight is this value. So her mass is going to be her weight divided by g, the acceleration due to gravity. Well, what is that? Well, it's 840 newtons. But remember, her weight force is pointing down. That's a downward force. It's a negative force, negative in value. And we'll just put a little negative sign there. And we have to divide it by g, which is negative 10 meters per second squared. Well, that means her mass, or m, is equal to 84 kilograms. Well, we know her net force is her weight minus 840 newtons, and we're dividing it by her mass of 84 kilograms. And this may seem like we're going in circles, and that's because we are. We're calculating her acceleration. Well, her acceleration is going to give us back that minus 10 meters per second squared, which is in fact g, which we'd expect. Her only acceleration is due to her weight force. Well, then her only acceleration would be g. You don't need to calculate it. If you just realize that, you could just write down her acceleration is minus 10 meters per second squared. All right. Part B, at some later time interval, now there's 520 newtons of air resistance. Well, air resistance is a form of friction. It's always going to be pointing in the opposite direction of movement. She's falling because of her weight. We've got her weight force, and we've got her resistance force, air resistance force up. And the weight is still bigger, so we keep that in mind, especially when now we're asked to get her acceleration again. Well, we do it exactly the same way. Her acceleration is her net force over her mass. Well, what is her net force? Well, her net force is going to be the sum of all the vertical forces, which is her weight force, but we know that's a negative value, plus her air resistance force, and since that's pointing up, that's a positive value. It's always important to remember which one's up and which one's down. Which one is up is positive and which one is down is negative, divided by her mass here. Well, we know all three of these values now. We know her weight is negative 840 newtons. That's the direction of the force and the magnitude, plus her positive air resistance pointing up is 520 newtons up, and then we divide that by her 84 kilograms of mass, and mass is always going to be positive. We add the two together on the top, we get minus 320 newtons of net force. In other words, it's still a force pointing downwards, just less than her weight, divided by 84 kilograms. And when we divide that out, we get an acceleration of negative, because she's still falling downward and getting faster and faster, just not as high an acceleration as before when there was no air resistance. And her acceleration is negative 3.810. And the units are meters per second squared, because that's what it always is for acceleration, including acceleration due to gravity. And that's her acceleration. Now, if we look at part C of this problem, her air resistance has increased even more. And we are told the net force on her is 0. Well, we know her weight didn't change. Her weight is still pointing downward with 840 newtons. That's a negative direction. And if her net force is 0, well, then her air resistance must also be equal to 840 newtons. Of course, this time it's in the positive direction. Well, her air resistance must be 840 newtons to balance those two out. So that answers that part of the question. And then we're asked to calculate her new acceleration. Well, her net force is going to be her weight force, which is negative, plus her air resistance, which is positive. And what do those equal to? Well, it's negative 840 newtons plus positive 840 newtons, which is 0 newtons. Well, acceleration is equal to net force over mass, and it doesn't matter what her mass is. She has 0 net force over top of her 84 kilograms, so she's going to have an acceleration of 0 meters per second squared. Or once you knew that there was no net force, you immediately know there's no net acceleration, and you could just write the 0 at that point. And then finally, we have a situation where she actually opens up her parachute. And what happens here? Well, she opens up the parachute and suddenly she gets a massive air resistance. Why? Because the parachute has gigantic surface area. It hits a lot of air at once, causing a huge amount of air friction, which is air resistance. So now we have a giant air resistance of 2,480 newtons, and that's in the positive direction, of course. And her weight is still there. Weight force is still pointing down with 840 newtons. Of course, it's in the negative direction. And if we want to calculate her acceleration after she's opened up the chute, just like before, it's the net force divided by her mass. Her net force, as always, is her gravitational force, which is negative, plus her air resistance, which is positive, divided by her mass. What does that equal? It equals her 840 newtons of weight, but remember that's negative, plus her enormous air resistance of 2,840 newtons, and that's positive. And we divide it by her 84 kilograms of mass. Well, if we add the top two together, we get an even 2,000 newtons of net force in the positive direction. In other words, the parachute is accelerating her upward. Divide that by the 84 kilograms of her mass, and you end up with a positive acceleration this time. It's huge, 23.81 meters per second squared. This is about 3 times the acceleration due to gravity, but in the opposite direction. So the force is huge, so our acceleration is going to be huge as well. And then the next question says, what phrase do we use to refer to the situation in part C? So part C, not the one we just did, but 2 back, when the net force is 0. When the net force is 0, the acceleration is 0, and that means her velocity stops growing. When her velocity stops growing, it's the last velocity she'll have. It's a very, very fast velocity, but it's not going to get any faster. It's her last velocity, so we call it her terminal, meaning last, velocity. Some people call it terminal speed, but we'll call it terminal velocity. That's the more common term. And what are the characteristics? I say to name at least 2. We can probably come up with 3 here. It's a constant velocity. She stops accelerating. Does that mean she stopped her velocity entirely? No, her velocity is still downward, and it's still very fast. Now, terminal velocity doesn't necessarily have to be very fast. It is fast for a human and a large object. the terminal velocity for a feather is still constant velocity. It's still downward, but it's not very fast. So the first two are the answers that are always correct of terminal velocity, and a terminal velocity of a person or a box or something with a significant amount of mass dropping through the air for a long period of time, long enough to build up air resistance, will in fact be very fast. Okay, let's look at the next problem. The next problem says Lily applies a 200 Newton force in the plus x direction, in other words to the right, to a 50 kilogram box on the floor, resulting in the box moving at a constant speed to the right. And we're to use g equals negative 9.8 meters per second squared here. And as always, we're asked to draw a free body diagram. So we have information here that says there's a applied force. So let's just put in our applied force right away. There's our applied force to the right. That's what we're told. It's in the plus x direction. We are told it is a 200 Newton force on a 50 kilogram box. So if it's 50 kilograms of mass, there must be a weight force as well. So we've got a weight force, F sub g, which we know in advance is m times g, little g. And then it says the box is moving at a constant speed to the right. Well, if we've got one force to the right, but it's not accelerating it, there must be another force to the left to balance it. And if it's at a constant speed, that means there is no net acceleration, and therefore there is no net force. So we know the force of friction pointing to the left must be exactly equal to the force applied of the 200 newtons. Well, we also know this box isn't flying up into the air, accelerating faster and faster, and it's not going through the ground. There has to be a normal force balancing the weight force. So we have four forces, and the two horizontal forces cancel each other. How do we know? We're at a constant velocity. And the two vertical forces cancel each other. How do we know? Because the box isn't accelerating up through the air or down through to the center of the earth. Okay, so we get this far, and we have our free body diagram. Now let's just fill in the values in our box. There we go, should fit everything in here. And we know our weight force is a negative vertical force, so we'll put that in there, and we know that it's m times g. We know the applied force is a positive horizontal force, and we actually know that value. And then countering these two, we know countering the applied force is a frictional force. We're not told how much friction, but we know it can be calculated with mu, the coefficient of friction, times the normal force, though we aren't given mu, so we have to figure it out some other way. And then we, scrolling up here just a little bit, we also have a force balancing the gravitational force, the weight force, of the normal force. And because the normal and the weight force are the only vertical forces, and we know they balance, they must be equal in size. So we can say that the two equal each other. So we'll put a little note here to say that the gravitational is the negative one and the normal force is the positive, just like the applied force is the positive and the frictional force is the negative in this case. And we'll label the gravitational force. So now we just add up the forces in each row to get the net force for both the x direction and the y direction. Well, the x direction, we already know the net force is 0 in the x direction. How do we know? Because it's moving at a constant speed along the floor. That tells us that the sum of the two forces, the applied, which is a positive number, and the friction, which is a negative number, must equal 0. And the same can be said of the normal force and the gravitational force. The normal force, which is our positive force, plus our gravitational force, which is negative, must also be equal to 0. And that's because the net force in this direction is also 0. So this is the first one is the x net direction. The second one is the y net direction. The line through there to separate the two. Sorry about that. Okay. So now that we have this basic information, we can use this to do our calculations. Scroll to the next section, and it says to show all your work, which we obviously couldn't fit in the boxes. And what are we going to solve eventually? Well, what we're going to solve eventually, if you look at part D, it says the coefficient of friction, mu. So let's list the things that we need to solve. Just like before, we've got a mass, which we know, an acceleration, which we do know, mu, which we don't know, and g, which we do know, and we're given the applied force. So we are told that the mass of the box is an even 50 kilograms, right? And we are also told that it has no net acceleration. In other words, it says it's running at a constant speed, so we know the acceleration is 0 meters per second squared, both horizontally and vertically if we were interested in the vertical. The square term in there, it's not letting me write the square. There we go. The mu we don't know. This is what we're solving for ultimately. Gravity is, the acceleration due to gravity is minus 9.8, like all accelerations, meters per second squared. And the applied force in this case is a positive 200 newtons. Okay, so we have a few of the non-force items up top, and then we have one of the four forces. Well, let's start calculating our other forces. We know we're going to need an F sub g, an F sub n, and an F of friction before we use that and calculate net forces. But we already know the two net forces are 0, so maybe we're going to use the net forces to calculate the individual forces in this case. All right, so let's go through it. We know the weight force, gravitational force, is m times g. And probably should just get in the habit of calculating that right away. In this case, it's 50 kilograms times our g, which is minus 9.8 meters per second squared. We multiply that out, and we get that the weight force is 490 newtons, and we know this is in a negative direction, so just put a note for yourself. And then we have the normal force, and since there are only two vertical forces, the weight force and the normal force, and we know it's not accelerating upwards or downwards, we know the normal force is equal to the gravitational force, the weight, but in the opposite direction. And so that means this will be equal to a positive 490 newtons. So you don't have to worry about the negative until the end. You just take note the normal force is pointing up, so that's the positive one. Okay, we got the two vertical forces calculated. Now it's time to calculate the individual horizontal forces. Well, the first one you don't even need to calculate. You were given it. The applied force is an applied force of 200 newtons, and it's in the positive direction. And that leaves the frictional force, which you know must be balancing the applied force exactly. If we were to calculate it, we would calculate it as mu, the coefficient of friction, times the normal force, but we don't know the mu. But we do know that the frictional force must balance the applied force. They must be the same value, but in the opposite direction. So that's also 200 newtons, but in the negative direction. So now we have all our individual forces calculated, and we happen to know that both of our net forces are zero. Our net force in our y direction is zero because it's not accelerating up or down, and our net force in our horizontal direction is also zero because we know it's not accelerating left or right. So we've solved for forces. What is left? Well, we still don't know the coefficient of friction, but we do know the formula for the coefficient of friction, or a formula that involves it. We know the force of friction equals mu, the coefficient of friction, times the normal force. Well, we know the frictional force is 200 newtons in the negative direction, and we know the normal force is 490 newtons in the positive direction. Well, we're not going to worry about directions because the normal force is vertical and the frictional force is horizontal, so we really can't use the positives and negatives. But in any case, when we solve for mu, mu can only be a positive number. So when we stick these values in, we have a frictional force of 200 newtons, really negative, but we're not going to worry about that, equals mu times our normal force, which is 490 newtons, really in the positive direction, but again, we're not worrying about that. So mu, we divide both sides by 490, mu is equal to 200 newtons from frictional force divided by 490 newtons of our normal force. And that works out to a ratio of 0.408. And there are no units because we are taking a ratio of two different forces. The newtons cancel out, and the coefficient of friction is a unitless value. So that completes that particular problem. And let's start on the last of the free body diagram problems in this set. So as you can see in this problem, it involves a helicopter. And if we read, it says a 4,600 kilogram helicopter accelerates upward at 2.0 meters per second squared due to the lift force by the propellers. Okay, there's a lot of information just in this one statement. 4,600 kilograms. Okay, it has mass, and therefore, being near Earth, it has a weight force. Even though it's floating up in the air, it's floating because its propellers are spinning, producing a lift force lifting it up. But there is a weight force pulling it down, and as always, the weight force will be calculated m times g, the mass times the acceleration due to gravity, which we are told is minus 9.8 meters per second squared. But if we look at the problem, it also says it's accelerating upwards, so we can put a little note here. You don't have to do this, but you can just remind yourself it's a plus direction acceleration of 2.0 meters per second squared. And what that tells us, if there's a net acceleration upwards, there's a net force upwards. Well, what forces upward do we have? We just talked about the downward weight force. The question states there is an upward lift force. They don't say lift force. They don't say the lift force is up, but it must be up if it's accelerating up, and it must be bigger than the weight force. Otherwise, it wouldn't be able to accelerate upward. And we'll just call that the force lift, and you can abbreviate it F sub L if you want. There are a number of different ways to describe this. So we've got these two forces. There are no horizontal forces because it's just moving up and possibly down. We're not talking about anything side to side. So this is the entire free body diagram. It's just those two forces, and we have to label them. Okay, so let's look at the table. Well, we have no forces in the horizontal direction, so we just leave those out. The net force, if we were worried about it, the force sub net in the horizontal direction, the x direction, is 0. As far as the y forces go, looking back at our free body diagram here, we'll just scroll back up. We have 2. We have the gravity down, the force of gravity down, so we know that that can go right in here, the weight force, which we know is a negative force, and we can just calculate that from the mass. We're given the mass, and we're given g. And then the upward force, if we look at our free body diagram, our upward force is the lift force. This is the force that the propellers put on the helicopter because they're spinning so hard, they're pushing down on the air, lifting the helicopter up. So we have a lift force that is clearly very powerful. Otherwise, we wouldn't be able to lift the helicopter against its weight. And not just lift it, we're actually accelerating it upwards. So we have 2 vertical forces, one up, one down. We'll label this one. We'll remind ourselves that's the positive one, and this is the negative one. And our net force in the vertical direction, which is really the only direction this is going to be moving, is the sum of these forces. It's the force of lift in a positive direction, added to the weight force in a negative direction. Well, that's pretty straightforward. Now let's look at the next page. It says show the calculations, so we didn't have any room in there. So now let's actually start calculating our forces. Well, before, when we were calculating forces, we had a number of things we were worried about. We were worried about the mass, we were worried about gravity, the acceleration, the coefficient of friction, which is no longer important. We're talking about vertical lift. Yes, you are probably pushing against air, but there's no mention of that here. So we're only going to deal with 2 forces, the force of gravity, which is the weight of the helicopter, and the lift, which is the force from the propellers. And the only 2 forces we have to deal with are the weight and the lift, and of course, the net force, which is in the y direction. Well, we are told, we look back here, we are told the mass of the helicopter is 4,600 kilograms, and the acceleration is plus 2 meters per second squared. So we can fill those things in right away. We know this is 4,600 kilograms. We know the acceleration is plus 2.0 meters per second squared. And we know gravity is minus 9.8 meters per second squared. So it's pretty easy from this information to calculate weight. Weight, as always, is going to be m times g. Well, what does that equal to? It's 4,600 kilograms, 4,600 kilograms times minus 9.8 meters per second squared. What does that equal to? Well, pull out a calculator, and you will find that it is equal to a fairly large number of newtons here. It's 45,080 newtons, and that's pointing downwards, so we have to remind ourselves that's a negative force. The other force is our lift force. Well, we don't have any direct information to calculate lift force, but we do have something very important. We have information to calculate our net force. And you might say, well, wait, there was no mention of the net force. No, there wasn't. But there was mention of 2 things in that statement of the problem: a mass and an acceleration. And this is Newton's second law. It's what we used to calculate acceleration earlier. Well, we know the mass and we know the acceleration. So we can just literally plug these 2 numbers in. The mass is 4,600 kilograms, and the acceleration is plus 2.0 meters per second squared. We multiply those together, we get 9,200 newtons. And that's going to be in the positive direction, so we have to make note it's positive. But we also know net force, being the vertical net force, is equal to the two vertical forces added together. Well, we have a weight force pointing down, that's our negative value, and our lift force, which we still don't know the amount of, which is pointing up. Well, we can plug these in. Our net force is 9,200 newtons. Our weight force, we scroll back up, we see our weight force is 45,080 newtons. So we fill that in, but that's a negative number, 45,080 newtons. And that leaves our unknown lift force. Well, if I add 45,080 newtons to both sides, 45,080 newtons to both sides, these disappear, and we have that our lift force equals the sum of these two values, which is 54,280 newtons, a huge amount of force by the propellers. The propellers generate a gigantic amount of force so that they can lift up the helicopter. And with this, we'll stop here.